All right, here we're looking at 7.1 for the stats class, and we're talking about confidence intervals. Now, today's assignment is about confidence intervals when the population standard deviation is known. So if we don't have that information, we're going to have a different approach we'll learn about later. But for today, if we know the standard deviation, the population standard deviation, this is the process we're going to use. We use this to calculate an interval that might contain the actual population mean. With a specific degree of confidence. So if you can think about it like, I think the population mean is somewhere around 3, but I'm not certain that it's 3. It could be 3.1, it could be 2.7. I need to create a window or a bubble around that, an interval where I feel pretty confident that the mean actually lives between those values. There's what's called a point estimate, and the best point estimate for the population mean is the sample mean. So if I take a sample of 45 people, I get the average from that 45, I can say, oh, that's going to be pretty close to the mean for the population, not just the sample. But I also recognize I could be off. Maybe my sample is biased. And so when I create an interval estimate, it's a range of values around that sample mean. It's possible that the actual mean for the population is there inside that range. It's also possible that it's not. You can kind of think of it like, okay, if the mean of a data set is, let's say, 3. This is my sample. If x bar is 3, and let's say I go up to 5 and I go down to 1. Well, it's possible that if I took a sample, or if I took the whole population as a whole, maybe mu could be 4.2, in which case 4.2 is right in there somewhere. Or it's possible that mu could be 5.3, which would be over here somewhere. So even though we create these bubbles or these intervals, it's entirely possible that our mu, our population mean, isn't actually in that region. But it's also possible that it is. The confidence level we have is the probability that the interval range is going to contain the parameter, the mean. Will the actual population mean be in there? If I say 90% confident level, then that's a 90%. That I'm 90% confident, or the probability that the interval contains the parameter is 90%. A confidence interval is calculated interval based on the sample data and the confidence level. So the common confidence intervals or confidence levels are 90%, 95%, and 99%. The whole idea here is that if alpha is the area that's left out of our confidence, so alpha is essentially what we don't have. Okay, this is the leftover. So if I'm 95% confident, then alpha would be 5%. That's the area that I'm not including in my confidence. In order to get it equally balanced, we take that alpha and we cut it in half so we can figure out how much is in each tail. If it was 95%, in the middle, I'm 95% confident that the mean's in there. I'd have 2.5% chance that it's above what I have, and a 2.5% chance that it's below my interval. The confidence level is always 1 minus alpha. That's why, if the confidence level is 95, alpha would be 5. And the formula for finding the confidence interval is x bar, your sample mean, plus or minus, because we have to have both tails, the right side and the left side, of your z of alpha over 2. We'll calculate that number in a minute, times the standard deviation for the population divided by the square root of the number of data values. And z of alpha over 2 is the maximum error of the estimate, or margin of error. We never let it get bigger than that. Okay, so commonly used ones, if it's 90%, it's 1.65, 95, it's 1.96. This would be your z of alpha over 2, and 99 is 2.58. If I wanted to do this by hand, let's say I go through the process of finding alpha for a 90% confidence level, I start by figuring out what area is left out. So if I'm 90% confident, then I have an area of 0.10. Now that has to be cut in half, so I put half on each tail. So when I cut alpha over 2, I end up with 0.05. That means 5% is on each tail. Now if I wanted to figure out where that number, what that would lead me to, what the z is for 5%, I'm going to go to the chart, the z table, and I'm going to look for 0.05. Now I know this occurs on the left side and right side, so I'm going to just look at the left side for 0.05. And so I'm looking for 0.05. If I was looking on the right side, I'd be looking for 0.95. So I'm just going to do it from this side, looking for 5%. There's a 0.05 there, but I'm looking for as close to 0.05 as I can get. And I can see there's one there, and there's one there. Those are my two numbers around 0.05. Now my confidence interval, the interval in there should never get smaller than my confidence level. So if I want 90%, then I can't have anything more than 5% in the tail. So when I look at the two of these values, I notice that this value is less than 5%, which means I have less than 5% in the tail. Whereas this number is bigger than 5%, meaning I have more than 5% in the tail. That's not good. We want to stay under that limit, okay? And so the value here is 1.65. And so if we go back here to our notes, that's why 1.65 is the z of alpha over 2 for 90%. And of course in the formula it uses plus or minus, so that's why we have a negative side and a positive side. But it's 1.65. An example of how to use this, a researcher wants to estimate the number of days it takes an automobile dealer to sell a car. Sample of 50 cars, that would be our n. Had a mean time, this is a sample, so this would be x bar, mean of 54. Assuming the population standard deviation, sigma, is 6, and we want a confidence level or confidence interval of 95%. So a couple of things. We start out using our formula. It says first, find the best point estimate. The best point estimate is the mean, or the sample mean, which is 54. That's our best individual estimate, but we're going to create an interval from that. And the way we do that is by taking our best estimate, 54, plus or minus, the z-score for 95% as an alpha over 2. Go back a page. 95% is 1.96. So I'll use 1.96 times the standard deviation, 6, over the square root of the sample size, 50. And if I put this into the calculator, let's go one at a time. You can't do the plus and the minus at the same time, but I can go 54 plus 1.96 times 6 divided by the square root of 50 and press enter. That's 55.66. That's on the plus side. 55.66. And in the middle of this interval will be the mean, the population mean. If I come back over here and do the same calculation, but I'm going to switch to a minus, I get 52.34. So that is an interval where I have 95% confidence that the actual mean, the population mean, is somewhere in there. Okay. Another example of this would be we've got 30 emergency room patients. That would be my n. Average waiting time for this sample, x bar, is 174.3, and the standard deviation is 46.5. We want a 99% confidence interval. So first, the best point estimate is 174.3. And to find the interval, we will take that 174.3 plus or minus. For 99%, the z of alpha over 2 is 2.58. That's times the standard deviation of 46.5 divided by the square root of n, which is 30. So we're going to grab our calculator, and we'll start with 174.3 plus 2.58 times 46.5 divided by the square root of 50, no, 30. Let me back up and make that a 30. You get 196.20, or 196.2, that's the upper side. It's less than, is greater than mu, mu is greater than, and we'll do the same thing, but go over and make it a minus. and 152.4. And there's our interval. We expect with 99% confidence that the region's there. Now, if I'd wanted less confidence, this region, this interval, would have shrunk. It would have gotten a little narrower and not so wide. This is a big gap of 40 minutes, 44 minutes. That's a big gap. The last thing that we're going to learn how to calculate is how big of a sample size you need in order to have an accurate estimate for the population mean. You know, you can't just say, hey, I'm going to take 3 people and use them as the average. You need more than that, depending on what you're trying to calculate. This formula uses n equals, so the number you have equals the z of alpha over 2, what level of confidence do you want, times the standard deviation, divided by what's called the margin of error. And then that all gets squared. So if I look at an example, in 7-4, it says the scientist wants to estimate the average depth of the river. He wants to be 99% confident. That's important. Accurate within 2 feet. This would be our margin of error. Okay, this here is going to give us our z of alpha over 2. Okay, the previous studies, the standard deviation of the depth was 4.33. So the formula says that n equals the z of alpha over 2. For 99%, it's 2.58. We times that by the standard deviation of 4.33, and that's all divided by the error of 2, and that's squared. So simple calculation, 2.58 times 4.33 divided by 2, and then we're just going to raise that to the second, and we get 31.2. Now I'm always going to round this number up to get an extra sample, so I'm going to say 32 is the number of samples we would need to take. So one last thing to kind of look at before we're done, and that's just to understand a little bit better what we mean by the 95% confidence interval. If you could imagine, we have a mean right here. This is the mean, okay? And if I were to go and take a sample, okay, of the data, say it's everybody's height, you know, I might find that the average height in the sample I took is right here, a little high, but because the interval is wide enough, the mean lives, the actual mean, which is this line going across, it lives within that bubble that I created around the mean. And you can see that works here as well, it works here as well. And if I'm 95% confident, then most of the time it's going to work. 95% of the time it's going to be right. But there are times when our sample is just not in line. Maybe we got a high sample where it was biased and we had just the tallest people in the building. We're all in the same room when we tested. Could be a lot of different reasons, but we end up with a sample that just has a mean that's too far away from the other mean. It's not likely, but it is possible. And so when this occurs, you know, we're worried about that. That's why we increase our region. We go up to 99% to try and prevent missing the mean in that region. All right, well, that's the idea of what we mean by confidence intervals and what we mean by a percentage of confidence. Good luck, guys. We'll see you in class.